So now we have this nice function that will never go below zero. It will never exceed one, regardless of how far negative these x values go or how far positive they go. Now we want to consider this notation called the odds. Undoubtedly, you have encountered this term if you're familiar with Las Vegas sports betting. Sports bettors rarely talk about probabilities, they usually talk about odds. The odds of the Packers beating the Steelers as 3/2. You can take any probability value, you can convert it to odds easily with this formula. You can also convert odds to probability. What's nice about odds is that you can represent it more simply. If you simply just start with this equation for probability and you plug it into this ratio right here, cancel out a bunch of terms, rewrite the equation, you actually end up with an equation that looks like this. And this becomes even nicer when we take the logs of both sides of that equation, because now we have something that is linear on the right-hand side. So just a note, whenever we see the log of odds, that's the logit. And when we see the word logit, just remember that is the log of the odds. So the logit is a linear function of the predictors. It takes values from -infinity to infinity, which means the x values can go from -infinity to infinity. The outcome can also go from -infinity to infinity. There's a relationship between the logit, the odds, and the probability. So if we were to graph the odds as a function of probability, we would see that it stays quite low until we approach 1, and then it shoots up to infinity. When you see a graph like this, just make a mental note that it makes sense to find the log of this quantity, because you can see a nicer spread in the values this way. And you can see here that here it goes from -infinity to infinity, the logit does, and it crosses 0 when the odds is equal to 1. Let's take a look at an example and apply this to data. So suppose a customer is approached by the bank, and the bank is offering the customer a loan. Rarely happens these days. The outcome is whether or not the customer accepts the terms of that loan, and predictors might be demographic information or information about the bank relationship. So if we partition the data with a 60-40 split between the trading and validation, which is, well, remember, we want to partition the data when we're doing predictive modeling. And we will create 0 and 1 dummy variables for the categorical predictors. Modeling the loan acceptance on income. So suppose that we're only dealing with one variable, that variable is income. We would start with a general model like this. This is our equation for probability, remember. If we would convert this to odds, convert that to logit. Now, using the machinery provided by XLMiner, XLMiner actually based on the data, it gives you these coefficients. Beta 0 is a constant. Beta 1 is the coefficient for income here. And you would just plug that into the equation, like so. So you can see here that regardless of the value of income, the probability outcome stays between 0 and 1. The very last step is to classify the observation. Remember, in the classification algorithm, the probability outcome is something between 0 and 1. To convert that, we need to use a cutoff value. With some given cutoff value, if the probability is greater, we classify the observation as a 1. So 0.5 is a popular choice to start with as the cutoff value, but we don't stop there. We need to take these additional considerations into account. We want to maximize the classification accuracy, maximize sensitivity. These are all Chapter 5 concepts. Especially, we want to minimize the cost of misclassification.